Hey everyone, welcome. In these videos, we're going to begin chapter 5. So hopefully you've done the reading for chapter 5. You can find the sections you should have read again on the lecture schedule, on the syllabus. And we're going to start covering probably the first half roughly of the chemical reactions lecture. So I'm going to share my screen with you and we will get into this. Okay. All right, well, we're going to start off with a new picture of a hike because we are starting a new lecture. And this hike is called the Walls of Jericho, as you can see. And it is also a hike we did in Tennessee when we went and visited Nashville. We did some hiking around there. And this was a wonderful hike. I think my favorite still was the Cummins Falls hike I told you about, but basically you hike down quite a bit. So on the way out, you hike up quite a bit. It's not a big loop or anything. It's just a down and back. It was a 9-mile hike round trip. So it was a full day of hiking. It was kind of cool when we did this again. It was in March, but it ends here at this beautiful pool, and then you can see the waterfall back in there streaming down, feeding the pool. So we got here, we stopped and ate lunch. Now, my husband had done some research on this hike, and we were told that you really should kind of get up back in here to see the waterfall. Okay, I can't really see this pin very well. They just encouraged you online. We read that if you hike back in there where the waterfall is, there's way more to see. And what's funny is there were some other people on the trail ahead of us, and we all got down here and they kind of looked at the waterfall and they're like, oh, pretty, looks cool. And they turn around and they hike back out. But we decided we were going to there were some rocks over here on the right side of the picture. We crossed those rocks and then we hiked back up where the waterfall is. And this is a picture now, about 180 degrees. We're looking down into the pool. Here's let me see if I can change the color. So there's that pool. And so now we're up behind the waterfall. We kind of hiked up some, so it's getting pretty, but there's something else that we saw. There's another hidden waterfall back behind all of this. And if you kept hiking back a little bit, there was this whole big waterfall that fed the smaller waterfall that went down into the pool. So it was a really great hike, very cool. Walls of Jericho, highly recommend it. It's about an hour and a half drive from Nashville. So again, it was a full day, but one of our favorite top hikes that we did there for sure. So, okay, well, let's get into the lecture material for today, chapter 5. We're going to be talking about chemical reactions, and the goal for today, we actually won't cover all 3 of these goals. We'll get into like the first 2, but we want to learn how to write chemical reactions properly and then how to balance them. So those are the main 2 goals for today. So we're really going to only cover these first 2, and then next week we'll actually start recognizing a few types, but we'll have more types of chemical reactions to recognize next week. So we actually will do a little bit of number 3, but we won't finish number 3 fully until next week. So the way I like to introduce chemical reactions is I kind of like to talk about how much I love to cook. So I love to bake, I love to cook. If you're like me, you love to eat good food. We do go out to eat, okay? I have several restaurants that I love to talk about, but I love to cook, and I think I got my love of cooking from my grandmother. On Sundays after church, we would always go to her house, and she would have these massive like feasts. I'm talking like Thanksgiving level style feasts, and it was just awesome. It brought the family together. It's just some of my favorite memories growing up at her house on Sundays after church for lunch. And so if you're going to cook, if you're going to make a recipe, you have to have, well, if you're going to make a meal, you have to have a good recipe, right? Some people can get in there and just throw stuff together and it turns out right, but I can't. So I need to have a good recipe. So I've got cookbooks that I really love, and a good meal begins with a good recipe. So if we're going to make a s'more, it's starting to get cool outside. Some people may have bonfires outside on the weekends or in your backyard. If you're going to make a s'more, what is the recipe for a s'more? Let's actually write that out. Well, if you're like me, it starts out with a marshmallow. And then what else? I love to do some of a chocolate bar. I'm telling you, if you put a little bit of mayonnaise on it, that's my favorite. Maybe just a tablespoon or two plus graham crackers. I'm just kidding, guys. Who puts mayo on a s'more? Are you kidding me? Although, when I was pregnant, I would love to tell people that I ate weird stuff because they'd be like, "Are you craving anything?" And I'd be like, "Yeah." I'm telling you, when my husband cuts grass and the smell of fresh grass, I want to go out, and I've eaten grass a couple of times, but only if you. Just kidding. I would not do that. People would be way freaked out. But sometimes women. Oops, I need the eraser. Sometimes women, when they're pregnant, they do have very weird like mineral deficiencies, and they do want to like eat weird stuff. Look it up on YouTube. I promise it's weird. But no, I do not put mayonnaise on my s'more, but I do put graham crackers. Some of you believe me. I want to know who believed me. Okay, and then you get a s'more. So this is the recipe, right? Now, this is a vague recipe, and you can edit it how you like. You can add as much of these things as you like. But if we are going to give somebody a general recipe, we need to be a little bit more specific, okay? Here's what we need to know. We need to know how much of each ingredient to use, what to do to the ingredients, and then how much of the final product. So if you're going to cook a meal for your family and you have 4 people, or if you're going to cook a meal for 10 people, the recipe is going to be different. You're going to have to scale it up, right? Proportionally, or scale it down if you don't want as much food as recipe says it will produce. But we need to know how much of the final product, okay? I'm a person, I love to have leftovers because I don't want to cook every night. So I will sometimes multiply everything by 2 and double the recipe in certain cases. And so let's write a specific recipe that has this kind of information in it. Well, typically you do 1 marshmallow. And then I usually do maybe a half of a chocolate bar. I like chocolate. Okay. And then obviously about 2 graham crackers does it. And if we do that, we know we're going to get 1 s'more. And what do we have to do to this? We can't just put it together. Nobody does that. You heat it up. You hold it over a fire. Okay, so we add heat. And I'm going to write this over the arrow. It tells us what we're going to do to the ingredients. And then we know that we're going to get 1 s'more. That's the amount of our final product. So this is kind of a silly analogy, but it's actually a very good analogy to walk you through how you write out chemical reactions and how specific and technical they need to be. So let's move on. Let's apply this to a real chemical reaction. Okay, if I gave you this sentence right here at the top of this slide, it says carbonic acid in low pH environments breaks down into bicarbonate. You guys should know what that is, the bicarbonate ion. It's a polyatomic that you had to memorize. A bicarbonate ion and a hydrogen ion. Okay, that's just H+. So now the actual chemical form of this is written below. Carbonic acid is H2CO3. Okay, and then we have our arrow, and it says in low pH environments, so we add that information over the arrow. At low pH, will break down into these 2 ions. Okay, now anybody, I have this picture of this blood drop here. This is actually a critical reaction for your blood buffer system. This right here is what keeps your blood pH in the range, that the physiological pH range that it's supposed to be in. If anybody knows what that is, physiological pH, blood pH is about 7.35 to 7.45, so there's not a lot of wiggle room here. Our blood has to be at a very specific pH, and this reaction right here, it's part of our blood buffer system, is what helps our bodies do that. Now we've got some arrows in here, so let's kind of start to break down this chemical reaction. What parts do we have on the right side and the left side? Well, on the left side, these are called your reactants. Okay, the pieces on the left before the arrow, these are always the reactants, and these are the substances that undergo any sort of chemical change. Then on the right is, these are called your products. And these are the substances that are formed, right? Now, one thing to note, we are not destroying things, we are just rearranging bonds, okay? So ionic and or covalent bonds, You can have both here. We're no longer just talking about ionic or just talking about covalent. We're talking about all of it together now. They are rearranged in a chemical reaction and they make new compounds, but we are not creating or destroying anything. Oops. Created or destroyed. We'll come back to that in a second. We're just rearranging the bonds. We're breaking bonds and we're forming new ones, but we have the same kinds of elements involved. All right, moving on. Let's fill this in. Chemical reactions often include the, other information, the physical state of the reactants and products. So we need to have reactants. We need to have what we do to those reactants. We need to know what products we're forming, but we also will indicate the physical state, okay, whether something is a solid, a liquid, or a gas. And there's actually 4 abbreviations. So you'll see these in your textbook. I just want you to understand them and I want you to know how to write them in as well. The abbreviations of the 4 states. So if we have a solid, obviously we're going to abbreviate that with an S. If something is a liquid, you're going to abbreviate that with an L. If something is a gas, a G. And then if something is aqueous, okay, it's like a solution, then we're going to abbreviate that with an AQ. We call it aqueous and AQ. All right. You don't actually see the example of that up here in this reaction, but what this reaction tells us is that we have solid sodium bicarbonate. Okay, it is a solid, and when you heat it up, it breaks down into solid sodium carbonate, water, which is liquid, and carbon dioxide, which is gas. Okay, so this is just a more complete way to express what's happening in a chemical reaction. And these abbreviations will come into play and be very important probably in more of the stuff we talk about next Tuesday, but you need to be aware of them. Okay, now I mentioned earlier that we're not creating or destroying atoms. This is actually governed by a law in chemistry. It's the law of conservation of mass. The law of conservation of mass. What that means is, you've probably heard this before, but mass is not created or destroyed. The amount of mass we have on planet Earth is the amount of mass that's always been here. Okay, unless like a comet collides with our Earth, right? But the same number and types of atoms we've had are the same number of types of atoms that will be. And they will rearrange and we can form new stuff, but we're not creating new atoms or destroying atoms as we live. So what that means relative to our chemical reactions and what we're doing today is that in a chemical reaction, we have to have the same number and type of atoms in the products as we do in the reactants. Okay, you have to have the same number of sodium atoms on the right side as you do on the left side. Same number of hydrogen atoms on the right side as you do on the left side. So if we can take the reaction we had on the slide previous and look at it, sodium bicarbonate, I have 1 sodium over here in the one I just underlined, but I see on my product side I have 2. That can't be. We can't all of a sudden have 2 sodium atoms when we only had 1 before. And if we keep looking, I see back on the left side I have 1 hydrogen in sodium bicarbonate. Well, on the product side I have 2 hydrogens in my water molecule. Again, we can't just create another hydrogen atom out of nowhere. So to balance these things, to make it the same number in kind of both sides, we can put a number out front of sodium bicarbonate, which is what you've seen, what you see has been done in this reaction just beneath. I put a box around this 2. And now that 2, I'm going to erase it actually so you can see better. This 2, I'll just underline it, applies to everything in this molecule. If we put a 2 out front, it means we're multiplying everything in my brackets by 2. So now I have 2 sodium atoms, I have 2 hydrogen atoms, I have 2 carbon atoms, and how many oxygen atoms do I have? I have 3 in the bicarbonate ion, but if we multiply by 2, now I have 6 oxygen atoms, okay, because I've multiplied everything in those brackets by 2. Now what I've done here, when I added this number, that is called a coefficient. Okay, it is a number placed in front of a formula to balance an equation. We can only balance chemical reactions with coefficients, okay? If I zoom in, I cannot change these numbers, okay? These small numbers that are tucked within the molecular formulas, these subscripts, we know them as subscripts, we cannot change those numbers or we're changing the compound that we've made. And we can't do that. Chemistry is the same. It forms the same stuff when you mix the same ingredients. So because we can't change subscripts, the only way we can change the number of stuff that we have to make it balanced is with coefficients, all right? And those numbers, again, they have to go out front. So if you're looking at this, we put this coefficient of 2 out front of sodium bicarbonate, and now you'll notice everything on both sides is balanced. We have 2 sodium atoms on the left, we have 2 sodium atoms on the right, 2 hydrogen atoms on the left, 2 on the right, so on and so forth with the carbons and the oxygens as well. And the end goal here, what we've just done, now we have a balanced equation. Or you could say reaction, a balanced reaction, a balanced equation, same thing. And that is where we have achieved, we've accomplished getting the same number and type of atoms on both the reactant side and the product side. Okay. So now we're just going to practice this. This is kind of all the, it's not all the new content we're going to cover today, but it is all we're going to cover with regards to balancing equations. Now we're just going to practice the things we've talked about. So let's look at this reaction on this slide right here. First off, how would you say it? If you see this on paper, you're going to say it in your head. What does it mean physically? So let's literally look at these reactants here. You, from exam 1, learned how to both write compounds and write formulas if given the name of a compound. So here you're given the formula. I want to know what's the name of these. So look at the first one. You have K2SO4. We know K is potassium. So it is potassium, and then you name the anion. Here the anion is a polyatomic. It is sulfate, so it's potassium sulfate, all right? So we have potassium sulfate reacting with, that's what the plus sign means, reacting with our second reactant here. And what is that? We have Ba. You might want to grab a periodic table. Pause this video if you don't have one near you. Go grab a periodic table. Okay, assuming you've done that. Ba is barium, and then Cl we know is chlorine, but it's the anion here. These are ionic compounds, okay? Here is your cation in both cases. So I'm just using the rules for ionic compounds to name these things. Cation, and this one is an anion. How do I know these are ionic compounds? Because we have metals involved. Okay, remember, we don't have metals involved in covalently bonded compounds. So these are ionic compounds because we have metals, and I'm just using the rules for naming cations and anions in the formulas. So we have potassium sulfate and barium chloride, okay? They react together, and they give us, what's my product over here? Potassium chloride. Remember, use the IDE ending for anions, potassium chloride and barium sulfate. Okay, I don't have any transition metals here. These are all main group 1 and 2 cations, so I don't have to use Roman numerals or indicate the charge by saying the number. I just have potassium chloride and barium sulfate because potassium and barium will always have the same kind of charge, so because of their main group placement. All right, so anyways, I just wanted you to be able to say that. And now the question is it balanced? Well, let's look. Right off the bat, I noticed that I have 2 potassiums, okay? And over here, I just have 1 potassium. So one thing you can do, and we're going to practice this a whole lot, write out all the types of elements that you have. I'm going to keep sulfate together as a group because I have it on both sides. There's actually a whole rule we'll talk about for why we can do this in a minute. But I have potassium, I have sulfate, I have barium, and I have chlorine or chloride. And I have 2 on the right side, but I only have, 2 on the left side, 1 on the right side. And then you could go so on and so forth with all these elements. So sulfate, I just have 1 on each side. Barium, I see that I have 1 on the reactant side, 1 on the product side. Chlorine, I have 2 on the product side, or reactant side, 2 on the product, or sorry, 1 on the reactant side. I'm getting my words all mixed up. 2 on the reactant side, 1 on the product side. Okay. So let's see. Here's what I notice. I need to double the numbers of these things and then everything will be balanced. And the easiest way to do that is you put a coefficient of 2 in front of that product. And now everything should be balanced. Okay, now I have 2 potassiums and 2 chlorines. Okay, so we will pause this for right here and we will pick up with the rules. There's 4 rules we're going to talk about with